part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to continue the discussion of Faraday's Law. I'll be working through a few more examples, the first one of which is that of a long straight wire that carries current I, which is a function of time. The problem here is to figure out what is the electric field at some distance s away from the wire. And we'll be making use of Faraday's Law. Which is the line integral of the electric field around a closed path is equal to minus the time derivative of the magnetic flux through the surface, or a surface, that spans that loop. Okay? So the question is, what surface, what surface do you choose? Well, we want to write down what the magnetic field is. We can make use of the quasi-static approximation. And therefore, at some distance s away from the wire, the magnetic field is mu naught I over 2 pi s and in a circumferential direction. So I'm going to make use of the right-hand rule to determine the direction of the flux. And notice that I am writing the current as a function of time. Okay, so what loop do we want to make? Well, let's say we take our loop to be rectangularly shaped and of length L. Suppose the left-hand side is the distance s naught away, and the right-hand side of the loop is the distance s away. Okay, so the electric field is going to be pointing in the same direction as the wire, or rather as the current flowing. So therefore, the top and the bottom parts of the loop don't contribute. We've only got the left-hand side and the right-hand side. So therefore, on the left, we wind up with electric field evaluated at s naught times the length minus the electric field evaluated at s times the length, and then we need to evaluate the right-hand side of the integral. So this is minus the time derivative. The only factor here that depends on time is the current, so I can pull that out of the integral. So we have minus mu naught over 2 pi, the derivative of the current with respect to time, and we'll have a length here because we want to calculate, evaluate the magnetic field over this loop. So we have the length, and now we've got to consider the s term. So this is ds over s prime. I mean, we really should put primes over there, so not be careless with how we treat the variables here. In any case, when I do the math here, that'll still give me a natural log. And therefore, the electric field evaluated at some distance s away from the long straight wire is equal to mu naught over 2 pi, the derivative of the current with respect to time, natural log of s plus some constant. Okay, and that'll be pointing in the Z direction. Now, if you think about this for a minute, there's a little bit of a problem with this expression as it's constructed. And the reason why is S, as S goes to infinity, blows up. Or the electric field, rather, blows up. As S gets very, very large. So where's the fault in this reasoning here? Well, the problem with this is that we've got we don't have a static situation anymore. We're making use of the quasi-static approximation. However, in this context, basically what we're doing is that we're assuming that whatever changes take place with the current are transmitted instantaneously to the farthest reaches of the universe. Now that can't possibly be. We haven't taken retardation into account. So the information of the changing current isn't going to be transmitted instantaneously. It's going to be limited, of course, and limited by the speed of light. So we bumped up against one of the limitations of this kind of analysis. In a forthcoming lecture, when we get into Maxwell's equations and we talk about the displacement current, as I'll show you, the displacement current is not difficult to derive, just using some reasoning. However, the one issue with Maxwell's equation, it kind of obscures any sense of there being a retardation. And so I'll show you that there's a little bit of a subtlety in how you should interpret the displacement current and basically how you should view the terms such as this, where you've got the change in magnetic field with respect to time. You really want to make sure here you don't think of this as being a source, rather you just think about the fields being coupled together, okay? Because ultimately it is the charges and the currents that give rise to the fields. So with that being said, we bumped up against the limitation here, and it's really a preview of things to come in terms of what we're going to have to take account of in the analysis. So let's move on to the next example. Let's say we've got a long straight solenoid. And I want to determine what is the electric field inside the solenoid and outside. So we'll look at the solenoid from the end. It is a long straight solenoid with tight winding and not close to the edges. Then the magnetic field will be uniform inside, will just be U naught times the number of turns per unit length times the current, and we'll assume that the current varies in time or changes in time. And that'll be in the Z direction. This is inside. And the magnetic field, due to a long straight solenoid, vanishes outside. Okay, so we want to figure out what's the electric field then. Well, applying Faraday's law on the left-hand side, we'll construct our Amperian loops to be circles that are coaxial with the cylinder. So in the interior path, we have 2 pi s, where s is the radius of the path, times the electric field. That's the left-hand side, Faraday's law. On the right-hand side, we have minus time derivative of the flux, times the area. Basically, I'm going to pull magnetic field outside because it doesn't depend on its uniform inside, basically. and that'll be in the circumferential direction. Now, what about outside? Left-hand side of Faraday's Law, once again, is going to give you 2 pi s times the electric field. On the right-hand side, however, we only get a contribution from within the cylinder itself. So that's why I have a factor of pi r squared, where r is the radius of the solenoid, as opposed to s. And that's equal to minus mu naught times number of turns per unit length times the radius squared over 2s times the derivative of the current with respect to time. And there's your answer. I next want to work through a problem that's, I think, really, really interesting. And it involves a solenoid. Basically, whenever you've worked out circuit problems in general physics class, I guess with very few exceptions, you assume that your circuit was powered by a battery. And that was the source of the EMF. Now I'm going to work an example where a solenoid that bears time-varying current is the source of EMF. And what you'll see is it kind of results in some, I would say, almost paradoxical type results. Okay? Let's move on. This next example is really interesting. Basically, the problem is to determine what do the voltmeters V1 and V2 read. And if you just shout out an answer right away, and that answer might be, well, obviously, because the voltmeters are measured across at the same points in the circuit, they have to have the same reading. And that's completely wrong. The reason why you might be tempted to say something like that is because you get into the mindset of using Kirchhoff's loop rules. And remember, Kirchhoff's loop rules hold only rigorously for DC circuits. And as we discussed in an earlier lecture, as if you have AC circuits, if you're talking about household circuits at maybe 60 hertz, Kirchhoff's loop rules apply very well with only a very, very small degree of error. Of course, as the frequency goes up, then you've got greater error in the system. Here, we don't have a battery in this circuit. We do have a solenoid, a very long, straight solenoid. And we're assuming that this solenoid carries a time-varying current, I of t. And we'll assume it's slowly varying as well. Okay, so if you've got a time-varying current, well, there's going to be a magnetic flux. Because we've got a very long, straight solenoid, the magnetic field is going to be uniform inside, but of course dependent on time. And the magnetic field is going to vanish outside. Okay? So again, we're ignoring any kind of end effects due to the solenoid. So if there's a time-varying magnetic field on the inside, there's also going to be a magnetic flux. I'm going to assume that the magnetic flux has a form of some constant alpha times time. By the way, this treatment was first published by a fellow by the name of Romer back in 1982, and it appeared in an American Journal of Physics article. So it's really a really nicely written paper, and it's very enlightening. So I urge you to go ahead and check that out. Anyway, I'm going to follow Romer's treatment here. So we're going to have a flux here of alpha times time. And I want to figure out what a V1 and V2 measure. Okay, so outside magnetic flux is equal to 0, so therefore time varying magnetic flux is going to be 0 as well. So the curl of E equals 0 outside of the solenoid. However, it's not equal to 0 inside. So you might say, okay, well, because the curl of E vanishes outside, well, the field must be conservative. In fact, it isn't. And the reason why is because sometimes I think in physics we get a little bit sloppy with mathematics. Any of the problems that we encountered back in electrostatics involved simply connected regions. But now, we have a multiply connected region. Well, if you've taken a mathematics course on vector analysis, you probably were told what simply connected means. And basically, it's if you take a contour in a region of space and you shrink it down, you can shrink it down to a point without leaving that region. Now, let's say I take a contour out here. That clearly shrinks down to a point. However, if I take my contour such that it encloses region 1, it doesn't shrink to a contour. So in fact, this topology that we're looking at here is not simply connected, it's multiply connected. And therein lies the difficulty. Because it is true, outside of region 1, curl of the electric field does indeed vanish. However, in region 1, curl of E is most definitely not equal to 0. And again, going along with Romer's treatment, he assumes that the positive magnetic flux is directed into the paper, so I'll say into the screen. Okay, let's take a look at a 3D simulation of this, just to kind of drive home the fact that the topology of the circuit is important. Here we see a long solenoid that carries time-varying current. Along with the time-varying magnetic field, there must also be an induced electric field. For an infinitely long solenoid, textbook problems tell us that the magnetic field vanishes outside. However, for a finite-length cylinder, there certainly will be a non-vanishing small magnetic field. So as a practical matter, the resistor should be placed on the midplane of the solenoid. Notice that the red leads from the voltmeters are connected to the same point, and the black leads from the voltmeters are connected to the same point. However, the readings on the two voltmeters will be different. We divide the circuit into two regions, inside the solenoid and outside the solenoid. Inside the solenoid, the magnetic field and the curl of the electric field are non-vanishing. Outside the solenoid, both the magnetic field and the curl of the electric field vanish. Outside, there's also a non-vanishing electric field. Moreover, the line integral of the electric field is not independent of path, and this is why the readings on the two voltmeters will be different. Okay, so Back when we were first talking about EMF and Ohm's Law and those kinds of concepts, I first pointed out that, you know, in cases, generally speaking, the topology does matter. I mean, we were concerned with surface charges. Now, there are certainly surface charges on this circuit as well, but it's not going to figure into the analysis. So we really are just looking at Faraday's Law and the effect of having a system that has a multiply connected region. Before we go and analyze this particular problem, I'm going to look at a simpler DC circuit, just for reference. We've got a battery, and we've got two resistors. We'll call this little r, and this is capital R, and then place the leads of the voltmeter across the resistor. Now in the laboratory, this is a straightforward exercise. Just place it across there, presto, you know what the voltage drop is across this resistor, capital R. Okay? And you didn't even think about anything else. That's just the way it was. I mean, the lines are equipotential, everything's good. Okay, but we need to justify why can you do this? Well, the answer is that the electric field is everywhere conservative. For this system. Why? Because of the curl of the electric field vanishes everywhere, okay? So therefore, I want to figure out what the voltmeters measure. Well, voltmeters measure the line integral. Of the electric field. And we'll say that this is point P1 up here, and this is point P2. We've got two possible paths. Let's see, we should call this, I'll call it D1 and D2, okay? So I'm going to take the line integral of the electric field from P1 up to P2 along path D1. That's equal to the same thing as taking the line integral from P1 to P2, but along path D2. In this case, the path that you take is independent because the field is everywhere conservative. Okay? And that's why you can make measurements, why it makes sense to say, well, this is the voltage drop across the resistor when you hook up the voltmeter in this fashion. Okay? And let's label these paths. We'll call this C1 over here, C1 prime, C2 prime, and C2. We'll call V1 equal to the line integral of the electric field going from A to B. And along path C1. I'll call V2 the electric field going from A to B, but this time going along path C2. And if I take the difference between those two, V1 minus V2, basically that is going to be equal to A to B, or C1, and that is going to be plus B to A along path C2. So basically you're going to go from here, boom, all the way down here, and back up here. So that is the electric field around a closed path. But because the field is not conservative, even though the curl vanishes outside, it doesn't vanish everywhere. It's a multiply connected region. And this, in fact, is equal to alpha. And again, the reason why we have just alpha is because of how we've defined the magnetic flux here. Be positive going into the board. Okay. So what else can we do here? Well, we can use Ohm's Law. To figure out what current flows. And that's equal to 1 over R1 going from A to B along path C1 prime E dot dl. That is also equal to minus 1 over R2 going from A to B along path C2 E dot dl. You see, we're assuming here that the voltmeters draw very little current, so our current is basically continuous through here. So there's a negligible amount of error by ignoring any current that's drawn by these voltmeters. We're assuming that they're very high impedance. Okay, so comparing this with this, well, we're not quite there yet because you see this integral is taken with respect to or along the path C1 prime, not C1 prime. So how do we justify going from this stage here, or rather using this down here? And the answer is, look at this path here. Okay, if I look at C1 and C1 prime, those two sections of the path don't enclose solenoid. So everywhere in here, the curl is equal to 0. So I am justified in saying, well, that's the same thing as saying along the path C1, and likewise, that is the same thing as saying taking the integral along path C2. So with that, I can make these two replacements. We have V1 over resistance R1, and that's equal to minus V2 over the resistance R2. And plus we know that the difference between those two readings is going to be equal to alpha. So I've got two equations, two unknowns. I can just do the math here, and I'll find that V1 is equal to R1 alpha over R1 plus R2. And V2 is equal to minus R2 alpha over R1 plus R2. So this is a really cool result, because it doesn't matter, even if you choose the resistors that have the same value, there's still, the readings that you get in the voltmeters are still going to have opposite signs. And of course, if the resistors don't have the same value, then yeah, you're going to have notice even more of a difference, not just in signs, but in magnitudes. So this is a really neat problem, because it forces you to start thinking about circuits in a more general way, rather than just looking at them in terms of DC circuits. You just apply Kirchhoff's loop rules and arrive at an answer. Here you can't do that. And the reason why is because the curl of the electric field doesn't vanish everywhere. Even though it vanishes outside the solenoid, it doesn't vanish inside the solenoid. And we are dealing with what is known as a multiply connected region. Okay, I'll leave that up on the board for a few more minutes. Okay, the next problem that I'm going to work through is making use of the analogy in the forms between Faraday's law and Ampere's law. So, Ampere's law tells you you take the line integral of the magnetic field around a closed path, that is equal to mu naught times the surface integral of the volume current density, and integrating over the surface that spans this loop. Okay, now we have Faraday's law. tells you that the electric field, the line integral of the electric field around a closed path is equal to minus the time derivative of the magnetic flux through a surface that spans that loop. Okay, so way back from magnetostatics, we also had the BocaPhysics law. Okay. Magnetic field satisfies Ampere's law, and here it is you can solve for the magnetic field in terms of volume current density using the BocaPhysics law. Okay, if I draw an analogy between the form of these two equations, I can come up with an expression for the electric field in terms of the magnetic field. So going from here to here, what changes do I have to make? Well, I see I've got mu naught up top, and I've got the volume current density, which basically I can write as the area. So this is current per unit area, it's just the volume current density. And that actually goes over to minus the time derivative of the magnetic field. So making these replacements here, I can write this as minus 1 over 4 pi volume integral minus 1 over 4 pi times the volume integral of the partial derivative of the magnetic field with respect to time crossed into the separation vector over magnitude of the separation vector cube. So that's kind of neat. Basically, you didn't have to do a lot of calculation here, a lot of derivation, to come up with an expression for the electric field in terms of the magnetic field. Okay, so let's look at a particular example here. Basically, I want to calculate what's the electric field on the axis of an iron ring that is wrapped in wire and which gives rise to a magnetic field B is a function of T. Okay? So when you first look at this problem, it seems extraordinarily difficult. So you've got an iron ring, and basically it's like a toroid, okay? And gives rise to a magnetic field. Just has that's just a function of time. And I want to determine what that is. So how do we apply what we've done on the left-hand side to this problem? Well, if you'll recall way back from magnetostatics, if you had a wire ring, we determined the magnetic field, actually not just on the axis, but we also came up with an expression for the magnetic field in terms of elliptic intervals. We're not going to go back crazy today. We're just interested on axis. Okay, so the magnetic field in that case It's just equal to mu naught I over 2 times r squared all over r squared plus z squared to the 3/2 power. Okay, so that's for magnetostatics. So basically what I'm going to do is, by analogy here, I'm going to take this form, and that's going to enable me to write a form for my electric field. So how do I go from one situation to the other? Let's see, instead of the current, see, that is equal to G times the area mu naught is going to go over to minus the time derivative of the magnetic field. Okay? So basically what I'm going to do is I'm going to substitute whatever's this in this expression, and I'm going to replace it with this term over here, and that will give me the electric field. And there's your answer. And again, I really hate using this character for the area, but basically we're kind of running out of letters here, so I'm going to just use this cursive as to indicate that that is the area, the cross-sectional area of my iron ring. Okay, so this is the area S here. Okay? So we started with what seemed like a really difficult problem, the electric field on the axis of an iron ring that's wrapped in wire, and it gives rise to magnetic field B of T. And just by basically using a result that we had from magnetostatics and by analogy, you can come up with an expression for the electric field really fast without doing any ugly calculations. Okay? Leave that up there for a minute before we move on to our final example of the day. The last example I'm going to work through today has to do with something called the frozen field line picture. And basically, it deals with a substance, plasma for instance, that's perfectly conducting. And the magnetic flux through any arbitrary surface that moves with the plasma is constant. In order to investigate fusion plasmas, researchers use something called the ideal magnetohydrodynamic model. So it's ideal hydrodynamics MHD, or ideal MHD for short. The ideal means that the conductivity is infinite. And that's a good approximation to make if you're dealing with plasmas that are in the range of temperatures necessary for fusion to occur. The conductivity is very good, better than copper, comparable to copper. And so we can make that approximation go a little bit step further and assume that it's going to be infinite. It's important because it enables you to investigate magnetic geometries. That are favorable for fusion confinement. It's basically probably about the simplest model that you can use. It's a single fluid model, and you can investigate such things as equilibrium and stability of the plasmas. So that's why people are interested in this. So with this assumption of infinite conductivity, again, that means that the magnetic flux through an arbitrary surface that moves with the plasma is going to be constant. And it looks like the magnetic field lines are basically frozen into the plasma itself. So what does the ideal MHD model look like? Well, these first equations will look familiar. Of course, you have the magnetic field is divergence free. We also have Faraday's law. And we have Ampere's law. And those are the only three that we'll be dealing with. And you might be wondering about, well, Gauss's law, we still have divergence of the electric field is equal to the charge density over epsilon naught. As it turns out, for the ideal MHD model, we make the assumption that the permittivity goes to zero. So basically, this is not going to figure into our framework. We're not saying, though, that the divergence of the electric field is zero, and we're certainly not saying that the electric field is zero either. We are making what is called a quasi-neutrality approximation. Well, plasma is basically an ionized gas, and certainly at fusion temperatures, it's fully ionized. So we're assuming that basically the total number of ions is roughly equal to the total number of electrons. And because we've also assumed that epsilon naught goes to zero, not only do we disregard Gauss's law in this framework here, we also will not have a displacement current, which we haven't gotten to yet, but there'll be one additional term there, generally speaking. Okay, so what else do we have? Well, we have an expression of the total number of plasma particles is conserved, and rho m here refers to mass density. We also have the momentum equation. So we have mass density times time derivative of the velocity. We have that inertial term, we've got the magnetic force term, and we also have pressure gradient term. So P is pressure. We also have Ohm's law, in a little bit different form. The electric field plus velocity crossed into magnetic field is equal to zero. And I'll show you in a minute how you arrive at this expression. And then last but not least, you also have equation expressing that there is, the evolution is going to be adiabatic. So this is time derivative of pressure over mass density to 5/3 power. Okay, so these equations, we made huge number of approximations to get to this stage, and even still, it's a very complicated calculation. But I'm interested in particular about the frozen field lines, so I'm going to make use of this equation, this one, and this one here. Okay, so how do we get to this Ohm's law? Well, we start with the current is equal to conductivity times the electric field plus V cross B. Now, before, or I should say a few lectures ago, we assumed that the velocity was small, so that term just dropped out. We're not making that assumption this time. We are assuming that sigma is infinite, and so therefore we'll wind up, and also the current is finite, so we'll wind up with E plus V cross B is equal to 0. And if you are looking at the electric field in a reference frame that's moving with the fluid, then you'll see that the electric field is actually 0, and that's a perfect conductor, okay? So this is how you arrive at this particular form of Ohm's law. Now let's look at Faraday's law. And I can make the substitution for the electric field, that's equal to minus V cross B. Is equal to the partial derivative of the magnetic field with respect to time, actually minus. So we got minus on both sides, those drop out. Okay, so we said we were going to have an arbitrary surface. Draw like this, and this is our surface over here at time t, and this is our surface S prime at time t plus dt. The change in flux between here and here is just equal to difference in the surface interval of the magnetic field at time t plus dt through this surface as prime minus the surface interval of the magnetic field at time t through this surface. Okay? Now, because the magnetic field is divergence free, I'm going to go ahead and attach these guys together. I'll call this joining surface, this ribbon, R. Now, what do you know about magnetic fields through closed surfaces? They have to vanish, right? Or rather, the magnetic flux through a closed surface vanishes because the magnetic field is divergence free. So therefore, I have the, if I look at time t plus dt, calculate the flux through each of these surfaces or add them all up, they have to be 0. So this is through S prime, this is through the ribbon that attaches or connects these two rather. And then I have the contribution from this surface here. So we're just looking at one particular instant in time at time t plus dt, okay? So the magnetic flux through that closed surface has to be equal to 0. And you might be saying, well, what happened to the minus sign here? This should be plus and you should have a minus sign over here. But remember, we're taking the normal pointing outwards. So the reason why we lose the minus sign is because we're pointing inwards to taking it to pointing outwards, okay? So let's substitute this up here. So we have dphi is equal to surface integral over surface S of the magnetic field evaluated at time t plus dt minus the magnetic field evaluated at time t. And then we've got the contribution from the ribbon. If dt is infinitesimally small, I can replace this by partial derivative of b with respect to time times dt. Now to evaluate this term, I'm going to draw this a little bit differently. Just going to flip things around here. We'll have surface S up here and surface S prime down here. And this will be the ribbon here. And we're interested in this little differential area here. This is dl, and this is v dt. So, the surface element is equal to dl cross v dt. I'm going to make this substitution over here, and furthermore, because this is already going to be first order, I'm going to also make another replacement. I'm going to replace this by b. Okay, and then we're going to substitute this in for the line element. So this will be dl cross v dt. And we can permute those quantities, so this will lead to minus line integral of v cross v dot dl times dt. Dividing both sides through by dt, we'll have the partial derivative of the magnetic field with respect to time, and converting this over to a surface integral, we wind up with the surface integral of the partial derivative of the magnetic field with respect to time minus the curl of v cross v. And if I look back over here, by use of the assumption of perfect conductivity and also Faraday's law, I can see this is equal to this, and hence the partial derivative, or rather the derivative of the magnetic flux with respect to time is equal to 0, and hence the flux through an arbitrary surface that moves with the fluid is going to be constant.